Here is the TA demonstration for electrolytic solutions. I'm going to show you how to properly fill your Hoffman apparatus. We have here our potassium sulfate. It is 0.1 molar and it already contains our bromothymol blue indicator. In order to properly fill this, you will add the solution into the top here. Notice that we have our 3 tubes right here, the one which we will be filling from, and then our 2 side arms where the demonstration will work. You can fill this apparatus one of 2 ways. You can either get the solution approximately 2/3 to 3/4 full in the side arms, such as right now. I can stop filling. And if I choose to stop here, I need to take my Sharpie and mark the level of the solution on the arms. That way, as the demonstration continues and gas is produced, you'll be able to clearly see the difference in the amount of gas produced. However, there is also a secondary option. You can fill all the way full in these arms, which eliminates all current air inside, which allows for a very clear demonstration of the production of gas. So now if I were to stop here, any volume of gas produced is very easily visible, as there will be no gas remaining in either of these arms. So you can choose to use whichever you would like for your lab. In this case, I will choose to use this where it is full. So now that I have the apparatus filled to the level that I want, I need to close off my 2 stopcocks on the side. If these are not closed, all the gas that you are producing will escape out of the stopcock. Now, you do not want to fill any more beyond the level in the tubes, since it is currently equal. You do not need to have any more solution up in this area. As the gas is produced, it will displace our solution further up, and that is why we have this here to collect any solution and not overflow. Here's our Hoffman apparatus for the electrolysis of water. I have filled it with potassium sulfate, 0.1 molar, that contains bromothymol blue indicator. Our bromothymol blue indicator is green when it has a pH of neutral. It will be yellow in the presence of acid, blue in the presence of base. So now I will explain our power supply here. When I turn it on, you can see I currently have it set to volts, and it is reading 18.01 volts. You can set it to be anywhere between 16 and 18 volts. I will keep it here since it is already at the maximum power. Now I will turn it off so that when I handle my electrodes, there is no power going through them. So now I will clamp my black cord on the left side, the red cord on the right. I've connected them to the electrodes that are sitting and exposed. Now I will turn it on and we will see what happens in our apparatus. So as you can see, there is an immediate color change. Our left side has become blue and our right side has become yellow. So this means we have a basic solution now creating on our left side and an acidic solution creating on our right side. You can also observe there are bubbles forming right off of our electrodes down here, so there is some form of gas being produced. Now that about 5 minutes has passed, you can see that there's an obvious reaction here on our left side, producing a basic solution and quite a bit of gas. We started with our solution all the way up to the top of the stopcock. It is now almost down into the tube. For our right side, we have the same. It is now an acidic solution instead of basic, and we are producing plenty of gas. We started up here in the neck of the stopcock as well, We are just now entering the top of our cylinder. As you can see, these stopcocks are slightly offset. This one is taller on the left side than the one on our right. So looking at it, it appears that we have formed more gas in our left cylinder than we have in our right cylinder. Let's give it several more minutes in order to see a more obvious reaction, and then we will come back and compare the two. So now that 10 minutes has passed, again we have our basic solution here on the left and our acidic solution here on the right. Both are forming gas, but it appears our solution on the left has formed about 1.5 to 2 times more volume of gas than our acidic solution on the right. You can see that because we have a taller neck here and we are quite a ways down into the top of the cylinder. However, our right solution has just barely gotten out of the neck of its stopcock. So I think this is a very good demonstration of our electrolysis of water. Here's our Hoffman apparatus after the electrolysis has run. We have already removed the gas from the system by opening the stopcocks once. Now I'll leave them open. So now we will need to drain our solution in order to reuse it for later. To do that, you can either take a large plastic beaker, drain into here, and then use a funnel to place it back into the bottle. Or in this case, since our apparatus is tall enough, I can go ahead and open my stopcock. Now that our solution is drained, I can go ahead and close my stopcock, move my bottle. As you can see, it is already starting to go back to the neutral color as the basic and acidic solutions rejoin and begin to become neutral. I can leave the bottle, and you can leave the neck open to let air come in and help neutralize the solution again, and then you may leave it out for the next TA. Here is our setup for part 1B, the electrolysis of potassium iodide. I have my power supply and multimeter here. I have my red cable with alligator clip connected to the positive jack on our power supply. Then from our negative jack on the power supply to our COM jack, we have a link between them. And then we have our black alligator clip connected to the 10 amp jack on our multimeter. We have our multimeter set all the way to the bottom, reading DC, measuring amps. And next, we have our potassium iodide. It is our 0.1 molar potassium iodide solution. I poured some into my beaker here. That way I can mix in my phenolphthalein indicator. I only need several drops of phenolphthalein indicator. I have chosen to use 5. Now we know that our phenolphthalein indicator is clear in solution, and our potassium iodide solution starts out as yellow. You can observe that from here and from our bottle. Now I can take the solution with indicator, add it to our U-tube. Next, I will need stainless steel electrodes. I have 2 here. One goes into each side of our U-tube. Now that we have our U-tube set up with the solution, we can go ahead and take our clips and connect them. Red will be on the right side, black will be on the left side. And now if we take a moment to observe the flow of electrons, we know that the electron will flow out of the right side of our solution through our electrode down our red wire and into our power supply through the positive jack. Then it will leave from the negative power supply into our multimeter through the COM jack. Then it will come and leave through the multimeter out of the 10 amp supply through our wire into the left side of our solution. Looking at this, we know that our red clamp on this side is functioning as our anode, and our left side with the black clamp is functioning as our cathode. Now that all that is set up, we can go ahead and turn on our power supply. It is currently switched and set down to amps, and as we can see, there is an immediate reaction here on our left side. We are getting our pink solution color, which is our phenolphthalein indicator showing our left side is becoming basic. And here on the right side, if you look at our stainless steel electrode, you can see that it is becoming a dark brown, which would be our iodine coming out of solution and depositing near the stainless steel electrode. Here on our multimeter, we are reading 0.38 for amps, and that has been the electrolysis of potassium iodide. Now we are on to part 1C, electrolysis of copper sulfate. So here I have my copper sulfate, I have my power supply and multimeter. This is the same setup as we just did with the electrolysis of potassium iodide. The red cord is still connected to our positive jack. We have our negative jack connected to the COM jack, and then we have our black clip connected to our 10 amp jack. Our copper sulfate does not need any form of indicator in it, so we can take and add our copper sulfate. We can add it directly into our U-tube. As you can see, the solution is a very deep blue. Now we can take and add our electrodes. Both of them again are stainless steel, as we just did with potassium iodide. We can take and connect our alligator clips to our electrodes, and now we can observe it yet again. We should still have the same flow of electrons coming through. So again, our right side is serving as our anode, our left side is serving as our cathode, and now we can observe what happens once we turn on the power supply. Right away, I can see bubbles forming on the right side of our stainless steel, which would be our anode side. Currently, there does not appear to be anything happening on our cathode. We will let this run for a little while to observe and record any changes that we have on our electrodes. So now that our reaction has gone for a little while, I'm curious to see if there has been any pH change. So I'm going to take some pH paper, and first I can take and dip it into my original copper sulfate solution. As you can see, the solution is between orange and yellow, showing that our solution is slightly acidic. This is because our solution is in water. Now I can take the pH paper and test both sides of my U-tube. As you can see, my left side is still orange and yellow, showing we have a pH of about 5. However, the right side, where our gas is producing, is actually red, showing that we have decreased the pH and become more acidic. Now that the reaction has run for a little while, I can turn off the power supply. And as we saw, there was a lot of bubbles forming over on our left-hand side, and over on our right side, you can see that our copper has actually deposited onto our stainless steel electrode. Now if I take and remove this electrode, you can see that no copper has deposited on the anode side. Now that we have these observations, we can go and see and think about what has happened in our U-tube. Here is our setup that we just had for our electrolysis of copper sulfate. As you can see, we had our right electrode, which was serving as our anode, was producing gas and did not have any copper deposited on our stainless steel electrode. I will save that off to the side. And then we had our left stainless steel electrode serving as our cathode, had some copper begin to deposit on the bottom of our electrode as well. I will save that off to the side. And now I am going to do one more run. This time I'm going to be taking a copper electrode placing it on our right side so that it serves as our anode. And I will again use a stainless steel electrode for our left side as our cathode. I will hook up the two electrodes. And now I can turn on our power supply again, and we will observe the differences of what happens when we exchange stainless steel anode for a copper anode. The first notable difference that we have is that there is no gas being produced on our copper anode. So unlike the stainless steel, there is no gas being produced on our copper anode. Looking at our stainless steel cathode, just as before, there does not appear to be any visible reaction going on in the solution, but we will let our reaction sit for about 5 minutes, just as we did before, and then we will observe the changes after the reaction has finished. Now that 5 minutes has passed, I will take and turn off our power supply, stopping the reaction, observing the differences between our two. Still no gas was being produced on our copper electrode. However, if we pull it out, we can see that it is actually losing copper from its surface that is entering solution. This is noticeable by all the flecks of metal that are currently in our solution. And then looking at our stainless steel electrode, we can see that there is a branch of copper crystals forming off the side of it that is now dropped into the solution. And as well, it again was getting plated with copper. If I remove this and grab my previous one to compare, looking at the two electrodes, copper is plated on both of them, and at first it appears as if our original electrode has more copper plated on it, but by looking at it from my angle, we actually have a very thick ring of crystals forming along the bottom and back of our cathode. Here is our second trial, here is our first. So actually we see that there is about twice as much copper depositing on our second cathode compared to our first cathode. Now we're moving on to part 2, our plating of copper. Here we have our copper plate and stainless steel plate. You will need to set these up in order to have them ready to put into your plating tank. Since we are the first lab of the week, our stainless steel plate is clean because that is how they are provided. If you are not the first lab of the week, you will need to go through the process to clean your stainless steel plate to be ready for this section. We have gone through and already pre-masked our stainless steel plate, and we intend on plating 0.3 grams of copper onto it. In order to do this, we have our plating tank, which we have filled with our 1 molar copper sulfate solution. Then we have our power supply and multimeter setup, just as we had before. So our black clip is hooked into the 10 amp jack, and our red clip is hooked into the positive jack of the power supply. We have set the power supply to be at 1 volt, as you can see, and we will be monitoring amps on our multimeter. We have already done our calculations in order to know the amount of time we need to let the stainless steel and copper be in our plating tank with the power supply flowing through it. We are going to be monitoring this using a timer to keep track of our time and watching the amount of amps we have here on our multimeter. We need to record any time that there is a fluctuation in amps. That way we can accurately change the amount of time that we are going to need in order to achieve our 0.3 grams of copper on our stainless steel plate. At 1 amps, we calculated that it will take about 16 minutes. So now to start, I will take my plates, add them, and then screw them tight. Our copper is on our right side, our stainless steel is on the left. I'm taking and attaching our black node to our stainless steel, serving as our anode, and I'm taking our red clip and attaching it to our copper, serving as our cathode. Now I have to be ready because the moment I turn on my power supply, I'm going to need to start my timer, and now I monitor my amps and my voltage. So I'm sitting at about 0.23 amps, and so I know that since this is 0.25 is about 1/4 of the rate that we initially planned, I need to take and multiply the amount of time we need, 16 minutes, by 4. So I know that this should take us about an hour and 4 minutes. Since this will take a significant amount of time, we can stop our recording here and come back once we are closer to our end goal. Now we are just about at the end of our time. As you can see, our amps have increased since when we initially started. I am waiting for now to turn off our power supply, and now everything is done. I can unhook my clamps. I have my record of time and amps that it took. So now I need to undo my plate, and I need to go and clean my stainless steel plate in water and acetone in order to get it ready to measure. As you can see as I drag it out, I have gathered copper on my plate, and you can see the copper plate has started to lose its copper surface. So here I have my stainless steel plate that I have deposited copper on. I have a water bath and an acetone bath here prepared. In order to get this ready for measurement, I need to take and dip my plate into the water, very slowly swirl around. This is to remove as much trace of my plating solution as possible with losing as minimal copper as possible. Next, I take this right from the water bath, take it into my acetone bath. Again, once it is in here, swirl it around, make sure that it is completely submerged. Now I can remove this from the acetone bath, set it onto my paper towel that I have here to let dry. Once the acetone has dried off from the plate, I can take and remeasure its mass in order to see how much copper I was able to plate and if we were close to the expected amount. Now that I am totally done with my plating, I have already measured the amount of copper that I have plated on my stainless steel. So now I need to clean my stainless steel plate to prepare it for the next lab. To do this, I'm going to need to take this and put it into my hot nitric acid bath for several minutes. In order to do this, I am going to be using crucible tongs. Note, I want to be using stainless steel tongs, as you can see by the silvery steel color. I do not want to be using copper crucible tongs, so always double check to make sure you are using stainless steel and not copper crucible tongs. I will take my plate, set it into my bath of hot nitric acid. As you can see here, we just witnessed the reaction of copper and nitric acid. Now I will let my plate sit in there for several minutes, come back, and then I will remove it and put it through my water bath. Removing my stainless steel plate from my nitric acid bath, you can see that there is now no trace of copper left on the plate. So I can take it now, go into my distilled water bath, and we want to rinse our plate thoroughly of any remnants of our 6 molar nitric acid. We want to make very, very sure that there is no nitric acid remaining on our plate, because nitric acid and acetone react violently. Now that I have no nitric acid remaining, I will move over to my acetone bath. Here is my acetone bath. So I will now place my plate down and remove the tongs that I used nitric acid in. grab it with my new pair of clean tongs, place it into my acetone bath, thoroughly rinse the plate, remove, and then place on a paper towel to dry.